This is Bob McFitridge with Beckwith Electric Company, and I'd like to welcome you back to our series on integrated volt-var control. Hopefully you finished up session 1, which was basically dealing with how do we economically come up with a business case to implement an IVVC system. Session 2 is going to be why an IVVC system is required in general. So, discussed in session 1, the primary goal of the integrated volt-var control scheme is to coordinate regulators and capacitors in order to flatten the voltage across the distribution circuit so that we can reduce it when needed, knowing that a reduction in voltage should translate into a reduction in load. Secondary goals are to also reduce the amount of line losses, therefore freeing up more system capacity for real power, and also to attempt to reduce the operations on more expensive equipment and also allow us to regulate the voltage using less expensive equipment from both an installation cost and also a long-term maintenance cost. So those are our primary goals. But why do we need to flatten the voltage? So integrated volt-var control is based around the distribution voltage. So before we can understand how we're going to implement it, we need to figure out why we need it. So in the electrical utility industry in the United States, utilities are governed by an ANSI standard that states that the voltage at any customer interface, which is typically at the revenue meter, the connection point between the utility and any consumer, that voltage, if it's on the 120 volt secondary side, must be maintained between plus to minus 5% of the nominal 120 volts, which translates into a utility must keep the voltage between 114 and 126. Now, that is a ANSI standard. Certain states will dictate even further. For instance, in California, you have to maintain the voltage between 114 and 120. And I know in Connecticut, it must be maintained between 114 and 123 and a half. So you can see when states dictate a different voltage, they are not reducing the low side of that range. It's always remaining at 114. What they are reducing is the high side of the range from 126 down to either 123 and a half or 120. So obviously the states see a need or a goal or a gain by reducing the voltage on the high side of the limit, and that's what we're going to explore. So that being said, we don't necessarily regulate to 114 to 126 because that voltage is on the secondary side here at the house. But all the equipment that we're going to use to allow us to vary this voltage is going to be placed on the primary side, whether it's single phase regulators, whether it's a low tap changing transformer, whether it's a switch capacitor bank or a substation capacitor bank. All of those devices or pieces of equipment are going to affect the voltage on the primary side. In this case, this appears maybe to be a 4 kV circuit. So we've got 4,000 volts here at the primary side, and then to get it to 120 volts on the secondary side, we are going to be stepping it down through these distribution transformers, and then we're going to cable it from the load side of these transformers to the actual house. And these transformers and these cables will induce a voltage drop. Now in general, a voltage drop is going to be reduced across the entire system because when you transmit current, it has to go through the system to get from the generator to the consumer, and that system has impedance, mainly in the forms of the cable itself carrying the current, and then the transformers throughout the system that are used to either step up or step down the voltage. And these cables and transformers have impedances. These impedances, by definition, fight the flow of the current such that we have a loss, and that loss is typically seen in the dissipation of heat and a voltage drop. Therefore, we will have a voltage drop from the primary voltage through the secondary transformer and the cable. Besides the voltage drop through the transformation itself from 4 kV to 120, there will be an additional drop because of the impedance of the transformer itself and of the cable. Most utilities will add 1 to 3 volts to their modeling to allow for that drop, and therefore instead of looking at 114 to 126, they're typically looking more in the range of 115 to 117 on the high side, and then bumping this voltage up typically to 127 to 128 volts. So realize as later sessions, as we start getting into settings, we are anticipating a voltage drop across the entire system, and we do need to accommodate for additional voltage drop once we leave our primary before it gets to the actual consumer. Any voltage drop that occurs after it hits the meter is the responsibility of the end consumer and not the utility. So the only voltage drops we're concerned about are the voltage drops getting it to this point and then getting it through the distribution transformers and to the meter. Once it hits the meter, any additional voltage drops within the customer facility are the responsibility of the customer. So, to reiterate, ANSI has 2 different ranges. Range A is where we typically need to be running. And for the US on 120 volts secondary, we're looking between 114 and 126. Now, range B can be entered for very short periods of time during emergencies. And in range B, we are allowed to drop the low end voltage to 110, and we can raise the voltage to 127. So in the cases of system emergencies, it is within the utility's rights to have the voltage go between 110 and 127, and typically short durations of time are typically in the 5 to 10 minute range. So, why do we need to regulate the voltage? Why are we trying to keep it between these 2 levels? Well, if the voltage gets too low, induction motors can overheat. So a motor is always going to draw the same output. If it's 100 watt, it's always going to require 100 watts. Therefore, if the voltage is lower, the current must be higher to maintain that same output. And the higher the current, the more chance of overheating. So at lower voltages, we are producing more current for induction motors, which can cause them to overheat. Also, motors require a starting torque. So if it's an air conditioning unit, that motor to get running at full speed requires a starting torque, which is much higher than once it gets up and operational. And if the voltage is too low, there may not be enough torque to get the motor to get into full speed, and it can stall, which would then draw exponential current. So we need to have enough voltage present to allow the motors enough starting torque to get up and operational. Also, if you have UPSs, they may be triggered by low voltages, and you may be bringing UPS systems online that don't need to be brought online. Finally, lighting can be dim. So those are some of the negative impacts if the voltage is too low. If the voltage is too high, the main impact is failures of transformers, whether they're distribution transformers on a utility system or whether they're transformers in appliances such as washers, dryers, refrigerators, computers. A lot of transformers have insulation, and at higher voltages that insulation will break down and you will decrease the life and possibly damage the transformer if the voltage gets too high. We will also be reducing the life of the incandescent light bulbs at higher voltages. And finally, increased loading on transformers with no load. So at higher voltages, you have higher magnetizing currents on transformers that don't have any load. So those are some of the reasons we don't want the voltage to get too high. So, why is the voltage changing? If we are generating it at a certain voltage level, why will it not maintain that voltage level? And as we discussed a little earlier, it is due to the load or the current flowing from the generator to the consumer through the grid, and that grid has impedance, as does the load, and the impedance causes the current to dissipate via a voltage drop and heat. So what we know is that the higher the amount of current, the more the voltage drop. And also, the further away you get, the more the voltage drop, because the more you have greater impedance. So with that being said, typically the customer closest to the source will have the highest voltage at any given time, and the customer furthest away from the source, if we do not correct for the voltage, will have the lowest voltage. And as the load increases, the voltage drop will increase, and as the load decreases, the voltage drop will decrease. So our goal with IVVC is to try to find equipment that we can put across that circuit that will minimize the amount of voltage drop. The reason we want to minimize the amount of voltage drop is obviously we can only reduce the voltage to the point where the customer with the lowest voltage is still above 114 volts on their meter. So if I have a 10 volt drop and I must maintain 114 at the lowest, that means at the highest I must be at 124, and therefore I cannot reduce the voltage that much. So the idea is to try to flatten the profile, which in essence is saying that we want to minimize the amount of voltage drop across the circuit. So what causes the voltage to drop across the circuit? Well, the very first thing is the actual voltage level. Most of the power is kVA, so the higher the voltage, the less the amount of current required to deliver that same amount of power. Less current, therefore, causes less voltage drop. So if we can increase our distribution voltages, we will reduce the amount of voltage drop by reducing the amount of current flowing. This is why we step up the voltage from the generator to high voltages such as 230 or 500 kV, and then step it back down several times to get it to the 120 at the site. Because we know at higher voltages we have less losses and less voltage drop. So a trend has been in the utility industry to start to replace the 4 kV systems with either 12 or 25 kV, and in some cases as high as 34.5 kV. Another way we can reduce the voltage drop is to reduce or eliminate the poor power factors. So the majority of the impedance that the current is flowing through is actually reactive impedance. The cable itself is typically a mixture of both resistive and reactive, but all the distribution transformers found on the system are almost 100% reactive. And a lot of the load, customer load, all the motor load is reactive. Therefore, reactive current has more of a fight going through the reactive impedance than real current. That being said, on a typical distribution circuit, reactive current will typically cause a 3 to 4 times greater voltage drop than real current. So if we can reduce the amount of reactive current that flows through the system, we will reduce the amount of voltage drop. So if we can clean up our power factor to where we only have real current flowing at unity, then we will definitely greatly reduce the amount of voltage drop. Another way we can reduce the voltage drop is to balance our load between the 3 phases. Any imbalance of load will cause a circulating current to flow, which will cause increased voltage drop. So the more balanced our distribution system is, the less voltage drop will be created. Cable impedances and the length of the circuit obviously affect the voltage drop because they affect the impedance. The more impedance, the more voltage drop. Shorter circuits have less impedance, therefore less voltage drop. Also, load. As we stated, the more current that flows, the more voltage drop that's going to occur. So those are the areas or the ways that we can control the amount of voltage drop. And obviously, if it's not controlled, the two customers are concerned would be the one closest to the source who may experience high voltages at low current levels, and the customer at the end of the circuit that may experience low voltages at high current levels. So those are the two areas of concern. Now, that being said, there are different types of load on the system, and that load will affect the way the voltage drops. So there is constant power load. In constant power load, such as a motor is always going to have the same output, and therefore if the voltage is lower, the current is greater, and with greater current comes additional voltage drop. So constant power load will create additional voltage drop if we reduce the voltage. Constant current load has no effect on the current drop because the current remains constant on that device regardless of what's going on with the voltage. So we're not really interested in constant current load when we're looking at voltages on the system. Finally, we have constant impedance or constant resistive load. And in that case, as the voltage drops, so does the current. So in this case, a lower voltage means reduced voltage drop. So obviously, we want to lower the voltage if we have a constant impedance system, but not if we have a constant power system. And that is why we need to have the capacitor banks on the circuit, is to supply the VAR current to the constant power devices needing it, so that the distribution system does not have to supply that, and therefore will have a unity power factor, so that when we go into a reduced voltage level, we are actually reducing the current, which is one of our primary goals. So, capacitor banks, again, reactive current is going to cause 3 to 4 times more voltage drop than real current. So if we can remove the need for reactive current, we can greatly control our voltage drops. So the majority of the impedances on the load and on the system are inductive, and therefore we would need capacitive to cancel it out. And the closer we can get that capacitive current to the inductive load requiring it, the less distance that current has to flow, and therefore the less voltage drop that will occur. Therefore, if we can use capacitor banks closer to the load, we can reduce the amount and the distance that the reactive current has to flow to that load, and therefore reduce our voltage drop. So, if we have too many capacitor banks, though, that is just as bad as too few, because now we will have, instead of excess reactive current, we will have excess capacitive current, and that capacitive current will flow back to the distribution substation to find inductive load somewhere else. So, too few capacitor banks means that we have inductive load that's going to need capacitive current from upstream, which typically means it's going to have to come from the generator and through the transmission system. So not only are we reducing the voltage drop on the distribution system when we reduce the VAR requirements by adding cap banks, but we will also reduce the amount of capacitive current that's required to flow from the generator through the transmission system to get to the distribution system. And that'll free up throughput on the transmission grid for real power to flow. So that's an added benefit on the transmission side we had talked about earlier. So there are only two sources for capacitive current. We either run our generators such that they output a combination of real and reactive power, and again, that also reduces the amount of effective output of the generator. Generator is rated for a total MVA, and therefore for every VAR we are generating, it's 1 watt we cannot generate. So, by reducing the VAR requirements, by having them located as close to the inductive motors as needed, we allow the distribution circuits not to have to carry that VAR current, which then allows the transmission grid not to have to carry the VAR current, and the generator not to have to generate the VAR current. So we are winning in 3 different areas of the grid by having the capacitor banks as close to the inductive load as possible. Now, hopefully now you've got a better understanding of why voltage changes. So the next area is how to correct it. One way you can correct the voltage is with the fixed taps on transformers. Whether it's a pole top transformer or a large transformer found in a substation, typically they come with fixed taps. And a fixed tap allows the transformer to either raise or lower the output voltage from the input voltage by a fixed percentage. Typically either raise 2.5 or 5% or lower 2.5 or 5%. The disadvantages of the fixed tap are, number 1, it cannot be dynamically changed. So this does not help with the load flow during the day as the load increases and decreases. We can't adjust the fixed taps accordingly. And also we can only change the fixed taps under no load. So the transformer has to be de-energized with no load on it in order to change the fixed taps. So fixed taps typically are not a tool that we can use in our toolbox to help regulate the voltage as the load fluctuates. So next session, session 3, we are going to talk about the different devices that are in our toolbox. And that would be with inside the substation fence, load tap changing transformers, bus regulators or feeder regulators, along with substation capacitor banks. And then outside the substation on the distribution circuits themselves, a combination of line regulators and pole top capacitor banks, both fixed and switched. So hopefully in session 2 we have given you a better understanding of why the voltage fluctuates due to load and impedances, and why we want to reduce that fluctuation so that we can flatten the profile and therefore allow us to reduce the voltage across the entire circuit. And we'll be covering those issues in future sessions in more detail, but hopefully we have a better general understanding. So we hope to see you in session 3 and at Beckwith Electric. We always thank you for your time and have a blessed day. Bye-bye.